Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Looking at virtual work, for this particular problem, we want to determine the equilibrium position, the angle theta for equilibrium, okay, as well as to determine the stability for that position, okay, all right, whether it is unstable or stable equilibrium, neutral equilibrium will determine the uh, stability. All right. Then from that, okay, to solve the problem, we will consider the potential function and differentiate it with respect to theta and set it to zero to determine the equilibrium position from solving the resulting equation. Why for the stability, to determine the stability, you will take a second derivative, okay, and solve the resulting equation, okay, to determine the stability. All right, so that we have the spring force. Okay, we have a spring here, the force acting like that. Okay, let's call the spring force F source with S, and it has this displacement S. All right, let's all right. So, and we are going to have this force is acting W, the weight of this member is acting through half of AB, and the length of AB is given. So we'll have this as H. Let's call it Y. All right. So having all this information, we can for the spring for the weight, we can determine the okay, this is W. Let's fix it, the weight, all right, for that member, so that Y is going to give us half, starting through half of the length, this AB, which has been given as 4 meters, all right, half times 4 is sine theta. So that's what that will give us. Now, haven't gotten that, so this VG, that's our gravitational potential energy, is going to give us W Y times Y, right? So for the spring, we can as well do for the spring. For the spring, we are going to have, okay, S is going to give us be equal to 4 again for sine 90, okay, sine 90, okay, so we are talking about the displacement there, all right, or the extension is going to give us 4 times 90 degree minus 4 times sine theta, okay, sine theta. So we have that. So this is the same thing as saying is equal to 4 into 1 minus 1 minus sine, okay, sine theta. So that's what we are going to have there. All right. So we can just we can have the elastic potential now, V sub with E is equal to the spring force uh, times the displacement we just looked at over 2, which is also equal to the spring stiffness K. Spring has a stiffness K. Okay, so you can do it, get it from here, that, so that the can get our potential function to be equal to uh, K, okay, over 2, okay, plus uh, V, sorry, So let's take this first, like putting this one. So we have it as v is equal to the um, uh, w y. Okay, so for the gravitational potential, then plus that, we are going to have that. All right. So if we plug in values into this, we are going to arrive at all the values that we have there. The weight of the mass of the block is given as 80 kilogram. So we have to multiply by 9.81. When we do that, we are going to arrive at V to be equal to uh, 1156. Okay, 569.6 sine theta. Okay, sine theta. All right, then plus 3200. All right, the spring stiffness giving us 400 newton per meter. Plugging in everything, we are going to arrive and divide in our division. We are going to arrive at this. Okay, into 1 minus uh, sine theta. 1 minus sine theta. Of course, know that for the gravitational potential side, we also included our uh, y. Okay, so just multiply everything there to have that value we have there. So we have this squared. So this is what we are going to have, so that we know that we can expand this. If we expand this, we are going to arrive at this to be equal to minus, okay, minus 400 for, okay, we're going to arrive at minus 4, okay, 8 30 point 4 sine theta plus 3200 plus 3200 plus 3200 sine square theta. Okay, and squared theta. So let's consider now the equilibrium position. Haven't gotten the potential function ready. We can so for the equilibrium position, we have this equilibrium, the v, the theta will give us we'll set it to 0, as we said earlier on. Set it to 0. So if we do that and we take our derivative, we are going to arrive at minus 480, 30, 30, okay, point 4 cos theta, okay, plus 3200 plus 3200 200 sine 2 theta, sine 2 theta. So remember, we have to equate everything to 0. So having done that, we know that 2 sine 2 theta is the same thing as 2 sine theta cos cos theta. All right. So when we do this, we are going to arrive at minus minus 480, 0, so 430.4 cos theta, okay, plus 3,200, all right, times 2 sine theta cos theta, 2 sine theta cos theta. So solving further, and we are going to arrive at cos theta. Solve this, we are going to arrive at theta to be equal to 90 degrees, 90 degrees. And of course, we're also going to arrive at, okay, to make it easy, because we are going to arrive at cos theta, because cos theta is going to be common from this equation. Let me just bring it out for you. So you have this to be minus 4, okay, 830, 0.4, all right, plus 64, 6, 4, okay, 0, 0, 0, 0 sine theta, okay, sine theta, okay. So this is what you are going to have actually equal to 0, all right. So it is from here we'll have you can see that cos theta is going to give you 0. So from there you can have theta to be 90 for there, okay. Then when you solve the inner equation there, that there, you are going to arrive at theta is going to give you 49 degrees, okay, 49 degrees. All right, so these are the two angles. Then we can test them for stability. For stability, we are going to have, if we take the derivative, if we take the derivative, the squared v, the theta, the theta, theta squared, and plug in our first value, okay, we have as 90 degree. If we do that, we are going to have theta being 90 degree, 90 degree. We are going to arrive at this to be equal to um, minus 1, 5, 6, 9, 69.6. You can see that this is clearly less than 0, so it is unstable, unstable. Then we can also consider when theta is equal to 49 degree. If we do that, we are going to arrive at this to be equal to uh, 2000. So plug it into the equation for the second derivative. 27, they're going to have 27, okay, 2.754, 5.8. You can see that this is clearly greater than 0. So for at 49-degree position, we are going to have a stable equilibrium. While at 90 degree, we are going to have an unstable equilibrium. Okay, so that these are the results.